Yeah, thanks, Osi. Good evening, good afternoon. My name is Ilhan Gurel, and it's a great pleasure to be with the HelSec community again. And today I would like to talk about TLS, DTLS, OpenVPN, WireGuard, and IPSec. And I would like to tell a little bit more about the protocol details and the best security practices. And hopefully, if the time allows, I would like to show you some demos in the end. Briefly about myself. So my name is Ilhan Gurel. I work for Ericsson in the CT organization, and my work is related to trust and confidential computing, practical use of cryptography, and the topics related to hardware and software security. Today, the agenda of my talk is as I would like to start with TLS and DTLS. I would like to a little bit tell you more about the protocol details, how they work, what are the differences, the vulnerabilities, the best security practices. And I would like to talk about OpenVPN, WireGuard, IPSec, and in the end, I would like to give you a summary, and I also would like to show you demos. I do have some demos. I did prepare some demos. At least some of them do include the use of some of those hardware-based security, like protecting of some of those keys used by those protocols and protecting them by using things like Intel SGX, TPM, and HSM. And that's basically the topic of my talk today. And now let's start with TLS. TLS, I think some of the things that I'm about to tell you here, I'm sure that you're all familiar with those things, but I would like to at least go through some basics, and maybe I would like to go into some of the details that you may find some of those information new. TLS stands for Transport Layer Security. Essentially, it's a security communication protocol between two peers that can provide confidentiality, integrity, and authenticity. And normally server authentication, but it can optionally include client authentication as well. It uses hybrid cryptography. I will let you tell you more about what does it mean, hybrid cryptography, when it comes to key derivation, the way how those keys are exchanged, and so on, and eventually how those ciphers are used to ensure confidentiality, integrity, and authenticity. As we all know, right now, we use TLS 1.2 and TLS 1.3, and TLS 1.2 is further described in RFC 5246, and TLS 1.3 is described in RFC 8446. And TLS is a protocol, it's a layered protocol, as we all know. And there's a record layer which encapsulates different kind of protocol messages, TLS protocol messages, which can be alert messages. Typically indicates if something goes wrong, one of those parties, either client or server, can terminate this TLS connection, and it can basically provide information about alert level and description of that particular problem. That's handled with those alert messages. And then we do have handshake messages. It's also known as Handshake Protocol. And that's the part typically that handles those exchanging some certain information between client and server, like some certain security parameters, like what ciphers to be used, what are the versions to be used. And in addition to that, and there are a bunch of other information that I would like to tell a little bit more later on. And of course, during that phase, client and server can authenticate each other, can agree on some certain cipher suites, and then later on, by driving some certain keys, they can switch to symmetric encryption and decryption, of course, by ensuring its integrity as well. So that part is typically handled by Handshake Protocol. And we have this change cipher spec messages. In TLS 1.3, they are there for compatibility purposes, but this is typically used for signaling that, okay, now we want to use different cipher now. Like, for example, if you want to change from asymmetric cryptography to symmetric cryptography, that can be indicated by using change cipher spec. And then when this handshake protocol and everything is done successfully, and then both sides, they do agree on some certain keys, and they know what kind of algorithms to use, and then they switch to symmetric encryption. Typically, this is actually both confidential integrity. And when we look at, for example, TLS 1.3, it uses some of those authenticated encryption and so on, like AES GCM or CHA-20 Poly 1305. On the right-hand side, I try to list, well, these are basically the handshake sequences, full handshake sequence from the relevant RFCs. As you can see, there are some significant differences between TLS 1.2 and 1.3. I do have a dedicated slide. I would like to tell you more about this. There are some certain improvements, and I would like to go through them more in detail with you. About DTLS, datagram transport layer security. It is defined in RFC 6347. From the protocol point of view, well, of course, when I talk about DTLS here, I'm referring to DTLS 1.2. And DTLS 1.2, from the protocol point of view, it is almost identical to TLS 1.2. It does run on top of UDP, and because of that reason, it takes care of some certain things typically taken care by TCP layer. Like as we all know, TLS runs on top of TCP. Such as, for example, it can reorder packets, it can handle packet timeout, it actually, one of the things it does something different than TLS 1.2. It sends, for example, client hello, then server responds with hello verify request by sending some security cookie. It expects client to respond with the same security cookie with another client hello message. And also it does handle the sequence number for being able to mitigate replay attacks. So DTLS 1.3 is still in draft state. It's being drafted right now. Of course, when we look at RFC 7925, you will see some certain recommended ciphers. And one of the things that I also would like to highlight here is that maybe before I go into this PSK, raw public key and X509 based identities, DTLS, I'm sure that some those who have been in this IoT domain, I'm sure that you may be familiar with DTLS, because like we have this LWM2M protocol runs on top of CoAP runs on top of DTLS and so on. So the reason why DTLS can be popular for IoT devices that it runs on top of UDP, and the UDP protocol stack is much smaller than TCP stack. You don't need to, like, since space can matter a lot when it comes to constrained devices. So I think that's actually one reason why DTLS is being used in the IoT domain. It can use different kind of identities like pre-shared keys, which is defined further in RFC 4279, raw public keys, and X509-based identities. And of course, at least when I did try them on some of IoT devices, I had to fine-tune some of those timeout values. Otherwise, this may lead to a kind of situation that it may resubmit some of those handshake messages and over again. So it does actually require some sort of fine-tuning as a kind of side note. Let me a little bit tell you more about Ssl and Tls versions and the vulnerabilities. I think this is something that you have seen in the past. But let me start with the older versions. Like we all know SSL 2.0, and that became public in 1995. In 1996, SSL 3.0, and then the work has been transferred to the IETF, and then TLS 1.0 was released in 1999. TLS 1.1 in 2006, TLS 1.2 in 2008. And after 10 years, like in 2013, the community started working on TLS 1.3, which became final in 2018, to be exact, in March 2018. When we look at those protocols, I mean, right now, I will be soon talking about the best security practices and the guidelines and so on. So right now, we are not supposed to use anything earlier than TLS 1.2. Like we just need to skip those. Like we just need to make sure that we don't use like SSL versions, TLS 1.0, 1.1, and so on. So the reason is that there are some certain known vulnerabilities, and typically those vulnerabilities do happen because of number of things, either because of the fact that some of those ciphers, like some of those algorithms, are used wrongly, or maybe modes of operations are used wrongly. Sometimes the use of weaker keys, etc., and so on. So there are a number of reasons, but let me at least go through them one by one. At least these are the ones that I try to list them as much as I can on the slides. So let's start with B's protocol. I mean, this is happening because of the fact that TLS 1.0 was using a CBC mode, cipher blockchaining mode with predictable IV, which is not good. And then eventually this was leading to this particular attack. So even though that attack was demonstrated in 2011, it was actually already known, theoretically it was a known attack. So, and then crime and breach, and also these are compression attacks, and then these are typical examples of how compression can go wrong when you are doing, for example, encrypting some data. And especially when you're compressing data to be encrypted later on, if an attacker is able to manipulate some part of this plain text data, that can lead to, for example, this crime and breach type of attacks. So like, for example, crime is happening because of the TLS compression, breach is happening because of HTTP compression. But if I may very briefly explain how this is happening, is that let's think about like HTTP headers, request headers, and also payload. Let's say that attacker is able to manipulate payload, but not the header, but they want to find out security cookies, for example, and so on. They can just add some certain data, and then they can see if there are some, if the ciphertext size is growing or not. And by looking at that one, they can see if there are any repeating patterns in the part that they are not able to modify. And by trying out, and by trying and so on, and they can actually recover some of those data, like, for example, security cookies and so on. So Lucky 13 is another attack. Again, it's happening because of the use of, like, if I may also mention one thing, that CBC mode, for example, can lead to this padding oracle attacks. That can allow someone to break those ciphertext quite easily. Initially, this poodle attack also happened earlier. This is happening because of this padding oracle attack. Even though this was fixed later on, like fixing this some certain issues that can lead to this attack, and then but then later on, those the researchers, they were able to find out like some timing leakages, and by looking at this timing leak, they were able to initiate the same attack based on timing. SMAC. And then we have this freak, logjam. Freak and logjam, they're actually, in a way, that there are two examples of how the use of weaker keys can lead to the compromise and so on. We have the slot and drone attack, for example. This is about like how you can downgrade this TLS versions and so on to SSL, or maybe vulnerable versions, and some other attacks like Sweet 32. Selfie attack, as far as I know right now, this is the only attack that affects TLS 1.3. It does basically it only happens when you are running TLS 1.3 server on one server, and on the same environment you are also running client, and so on. And by using that kind of setup, they can initiate the selfie attack. During the Real World Crypto Conference back in January 2021, they did announce this Raccoon Attack. This happens while using Diffie-Hellman keys, not actually elliptic curve Diffie-Hellman, Diffie-Hellman keys. And eventually, by looking at some of those timing issues, and they were able to initiate this Raccoon Attack and so on. So these are, at least at very high level, some of the well-known vulnerabilities and attacks that are affecting SSL and TLS versions. And one thing that I also would like to highlight here is that, for example, when we think about a secure communication protocol like TLS with different versions and so on, used by billions, maybe reviewed by millions, and so lots of people are looking into the details of those protocol details, and I think it is still possible that something can go wrong, and that very much highlights the importance of how designing a secure communication protocol can be difficult. I mean, that's one example that I would like to mention. Let me also a little bit tell you more about TLS 1.3. So as I mentioned earlier, it became final in March 2018, and it took actually started from 2013 to 2018. It took like 5 years. The reason why it took a long time, as far as I can see, and also stated by others, is that TLS 1.2 and below followed the design, release, break, and fix cycle, whereas TLS 1.3 followed design, break, fix, and release cycle. I think it's holding well, as far as I can see. So what are the main differences between TLS 1.2 and 1.3? So first of all, this TLS 1.3 got rid of this static RSA-based handshake. It got rid of all those like weaker like any algorithm that can lead to like AES CBC mode is gone, and then MD5, SHA-1, RC4, and so on, they're all gone. Removal of compression, downgrade protection, and it only uses authenticated encryption, whether AES GCM, AES CCM, or CHA-20 poly 1305. It does also use this RSA PSS padding for signing for RSA signatures, and it does also use some new algorithms, elliptic algorithms such as ED25519, ED448. I mean, these are the new like ED DSA algorithms, and not only efficient, but they also come with much better security properties as well. One of the thing that TLS 1.3 introduced is zero round trip time. So that's basically a client can some information and they can immediately switch to some kind of like symmetric encryption, decryption, and so on. So zero RTT, even though it can significantly reduce some kind of like time to establish some kind of secure communication channel, but please just to keep in mind that else if you also look at the RFC 8446 and so on, zero RTT also comes with the price of some certain types of attacks, like for example, replay attacks. And so on. For that reason, it should be used carefully. I mean, I just wanted to highlight that one. If you also look at some of those well-known, like best security practices published by some certain organizations, you will also see their recommendations on that as well. One of the benefits of TLS 1.3, I think it's one of the most important benefits, that privacy. Like what it does is that typically, like when we think about TLS 1.2 handshake, all those messages, they are not encrypted. Whereas in the TLS 1.3, like all the messages after server hello, they are encrypted. I will also tell you a little bit more about encrypted client hello. It's also possible to encrypt some part of those client hello extensions. And by doing so, I mean, you can essentially hide information such as to which server you are making connection, etc., etc. So that can bring some certain privacy benefits as well. I will tell you more about this soon. So maybe before I start talking about the best security practices, at least what do we mean with really what the best security practices are? So when we talk about it, so obviously we need to talk about forward secrecy. So meaning that if someone steals your keys, then I mean compromise of this key will not let attackers to hide, for example, to steal some of the previous data and something like that. So you will basically have some kind of forward secrecy. And only this kind of like the compromise only will be limited to this particular session. The use of recent protocol versions, TLS 1.2 according to the security practices, or TLS 1.3. And being able to secure keys at rest, in use, and in transit. And then when I talk about keys, I mean, when we think about TLS handshakes and what keys are being generated, okay, there are some certain keys, they are like static keys, they are long-living keys, like these can be like RSA keys or ECDSA keys. But at the same time, we do have those ephemeral keys that are generated on the fly, like ECDH keys and key pairs. And obviously, they do actually derive those symmetric keys. Protection of those keys, they're also very important. How you protect them in use, maybe I will tell you more about during those demo sessions. At least I want to tell you what kind of technologies, for example, you can use to protect them at rest and in use. And also the use of strong and cryptographically secure keys. What do we mean with cryptographic secure keys? They were generated kind of like by using good level of entropy, and that's actually what makes them cryptographically secure. And so by using like good low level of entropy, by the use of like true random number generator and the cryptographic secure pseudo random number generator and so on. The use of secure crypto libraries is very important. And being able to use them against all known vulnerabilities and attacks is very important. And as you remember that I was talking some of them in my previous slides. Secure key generation is also related to this key management part. And the use of secure ciphers is very important. Like for example, the use of secure ciphers, meaning that can eventually provide us this forward secrecy, but at the same time, we can use those keys securely to authenticate, to do this authenticated key exchange. We can do this key exchange, derive keys securely, and so on. Like we can use, for example, well-known like secure algorithms, and then later on being able to use those secure ciphers like GCM or CHA-20 poly1305 and so on. Yeah, trust is very important when it comes to the use of, like when we think about the TLS protocol, right? Like a server authentication, server can authenticate itself by using X509-based certificate issued by a non-CA. Also, client can actually optionally can also authenticate itself based on certificate-based authentication. How those certificates are enrolled, how they're by whom. I mean, these are very important things and so on. And in addition to managing those secure PKI operations, and what is also one important is that how can you make sure that you can also handle those revocations, for example, certificate revocations. This is the something that I will be a little bit talking more soon about, like this, where we see OCSP stapling, for example, being used as well. So secure PKI operations is there very important. And now let's talk about the best security practices. So there are really well-established guidelines right now. I mean, not only some of those RFCs such as 7525, such as RFC 7540, and in addition to that one, like there is this RFC 7925. In addition to that one, some certain organization did actually publish quite good guidelines as well. And one of them is the German BSI, then the Netherlands NCSC. That's very good IT security guidelines. And also NSA published some recommendations quite recently that's essentially recommending to replace obsolete TLS protocols. And also they do also recommend to immediately block and disable all quarantine devices supporting those old protocol versions. These are the things that, I mean, these are very available, like publicly available. I do recommend you to have a look at them. They do include really good information when it comes to, for example, what kind of ciphers to use, software like random number generation and something like that. And also they do also include, for example, good information about like what do we mean with those ciphers, what part is for key exchange, etc. So there are some good information available on the internet. This is about this NSA link that I was referring. There are actually, they do also refer to some certain GitHub location that where you can find some tools as well. Anyways, this is there are good best security practices available. I think it is it's very important that being able to follow them will definitely increase your TLS, like the use of TLS protocols as well, DTLS as well. So I also would like to give you a little bit statistics. So these are the statistics which I was recently looking at. It's from SSL Post Statistics, and they're based on 150,000 websites from Alexa's list of most popular sites. As you can see here, like if you look at those versions being used, I mean, we can see that, okay, TLS 1.2 is the most commonly used, like 99.4% of those servers do support it. TLS 1.3 use is increasing steadily. But unfortunately, when we look at some other products, like there, you still see some use of TLS 1.1, TLS 1.0, even SSL version 3.0 and SSL version 2.0. So things, they don't look good when we look at those statistics, as you can see here. Some of them, they are actually grade F, meaning that they are exploitable, misconfigured servers. They use unsecure versions of those protocol and weak keys. When I talk about weak keys, I'm talking about keys such as like 1024-bit RSA key or something like that, even weaker than that. So some of them, they still use cipher, like stream cipher RC4. We know that RC4 has been, I mean, is known to be broken. And the good thing is that some of them, they do support OCSP stapling, and some of those servers, 34 of them to be exact, they still use some cryptographic implementations that are vulnerable to heartbleed attack. And as you may remember in the beginning of my talk, I was talking about this TLS 1.3 and its privacy benefits. TLS 1.3, I mean, this is, as a side note, Cloudflare has a great blog, and this, I put the link here. So as you can see, what does the TLS 1.3 does is that, like, as I mentioned earlier, it does basically encrypt anything after server hello, and all those handshake messages will be encrypted after server hello. So meaning that if anyone actively looking at, like, for example, this TLS handshake traffic, they will not be able to see the server certificate, for example. And that will enable, well, that will basically essentially allow someone to hide there, for example, like they won't be able to see to which server you are making connection. But this still requires additional protection. It's not complete. For that reason, there is a work going on. It's called Encrypted Client Hello. So what this encrypted client hello is that there is an IATF draft right now. So what it does is that it does actually encrypt some certain part of those client hello messages, such as, for example, server name indicator and something like that. So once this is encrypted, so initially they will do some key exchange in the beginning. Hopefully during my demo, I will show you the details, handshake details during my demo. But anyways, once these parts are encrypted, anyone, for example, anyone who is looking at this traffic, they will not see to whom you are making, to which server you are making connection. They will just see that you are making connection to one IP address, but in some cases that doesn't mean much, to be honest. So it can significantly improve privacy. That's something that I wanted to mention. Folks, this is also a post-quantum safe cryptography is a buzzword nowadays. I mean, I just wanted to put one slide here. That's something that I have done some experiments earlier. I also put the links here. You can also have a look at yourself. I think there are already some good information and good, there are some certain libraries, and so you can easily take them and use those things. So it is possible to use TLS 1.3. And by using some of those post-quantum safe algorithms. At least on my side, I did try it with Picnic and Frodo KEM algorithm. So one of the things which I've noticed when I use, like the purpose that why I wanted to try it out is that I just wanted to see those signature sizes, key sizes. But in addition to that, I wanted to see how much performance difference there will be comparing to, for example, non-post-quantum safe algorithms, like anything like ECDSA, ECDHE, ASGCM 256, and SHA-384, etc. So what I have seen is that, okay, first of all, Picnic, at least that particular variant of Picnic, generates very large signatures, like almost 32 kilobytes. And so, but I haven't seen much performance, big performance yet. And please keep in mind that these are probably reference implementations. I think that obviously if they are somehow improved, like probably they will be reasonably acceptable in my opinion. But anyway, I just wanted to mention this particular information here in case if you want to have a look at those things later on yourself. And I will share my slides, by the way. All right, so that concludes my part about TLS, DTLS. Now I would like to tell you a little bit more about OpenVPN. And now I want to tell you a little bit more about VPN protocols. And OpenVPN is a VPN protocol, as you all know. I'm sure that many of you have been using it and so on. It's a tunneling protocol, and meaning that all those packets, for example, they will be tunneled through into this UDP. You can also potentially use TCP as well. So when we look at the protocol itself, and it does consist of two parts. Like one of them is control channel, and another one is data channel. And as a side note, by the OpenVPN is a user space-based VPN protocol. Control channel is the one that can basically control, like to initiate, for example, this, you can initiate this OpenVPN connection, etc. and so on. And during this control, like during this phase, the control channel is also using TLS as well. So in addition to TLS, so the TLS is used here for authenticating parties, client and server. In addition to that one, also TLS is used for being able to exchange some key material. And what also OpenVPN does also quite in recent versions, at least the one which I'm going to use today, it's version 2.5.1. It does have something called TLS crypt, or also there is something called TLS auth. Like it is possible to protect this control channel, either it's confidentiality or integrity. It does actually allow you to that one. So with, for example, by using this TLS crypt, you can actually establish actually two levels of encryption, actually one TLS, and on top of that, you can basically encrypt the entire control channel as well. Yeah, so you can, by using this control channel, you can reset client and server, you can do acknowledgements, and eventually you can basically exchange enough data, and then you can basically exchange data on this data channel as well. So this is one of the things that that I also would like to mention here is that it is very easy to set up. In my personal opinion, it's very easy to set up this OpenVPN. And at least I would like to go through some of those configuration options that I have used. For example, how I'm running the server, with what kind of configuration, and the client as well. And I can, for example, in this configuration, both on client and server, I can specify what TLS versions to use, what kind of cipher suites to use. And so it gives me that level of flexibility. And one of the nice things, and I hope that this demo will actually work, is that you can use, for example, PKSS11 interface, and that's what I would like to do. So it can allow you to protect you, allow you to use some of those like hardware-based security, in this case HSMs, or it can be anything that can be accessed by PKSS11 interface. And now this is about this sample configuration that I was referring. Like you can run it in either tunneling mode or tap mode. When you run it in tap mode, so all those Ethernet frames will be basically tunneled. And then you can run it on different kind of, like whether on TCP or UDP. And you can actually, so that, for example, both client and server, if you want to use this TLS script, they need to exchange some certain keys. It's a kind of pre-shared key. But that TLS script version 2 is actually works differently than TLS script version 1. So this TLS script version 2, so okay, client has its own this PSK, like shared key, but at the same time, this shared key is also encrypted with the server's key and so on. So also during that initiation process, also client will send this encrypted key to server and so on, and then the server will decrypt and use it. So it's very similar to some encrypted security cookies and so on. As you can see here, I can actually specify what kind of TLS ciphers I would like to use, and also what kind of cipher, like I do state here that I will use AES 256-bit AES GCM, for example, Galois country mode, and that's authenticated encryption, and also minimum TLS 1.2. In my demo, I will be using TLS 1.3, and by providing some information about PKSS11 providers, it does allow me to use any kind of underlying hardware via PKSS11 interface. Okay, now let's maybe talk about WireGuard. So WireGuard, it has been quite popular ever since it became part of Linux kernel. But yes, I mean, WireGuard uses secure and fast crypto algorithms. And if I may elaborate a little bit further, that it uses curve 25519 based elliptic curve Diffie-Hellman based key exchange. It uses Blake 2. As you know, Blake 2 was one of those the NIST's SHA-3 competition candidates. It's based on Chacha-based construction and so on. It was designed somewhere back in 2012, but nowadays, recently, there's also Blake 3 version 3 as well, which has very impressive performance figures. For as authenticated encryption, it uses Chacha-20 and Poly 1305. And also, one of the things what it does is that it uses pre-shared key, and that pre-shared key will be used for key chaining. It's going to use this HMAC-based key derivation function. WireGuard, based according to their website and also published by a number of researchers, it is formally verified. So what is really formally verified is that both protocol and C implementation is formally verified. And at least according to the information, the C implementation of this curve 25519 is actually formally verified. In addition to that one, I think as far as I know, they also did formal verification of the protocol itself by using Tamarin and also ProVerify, as far as I know. But you can have a look at their website. They do have very good information. It is based on the noise protocol framework. I do have a slide next time. Next slide I'll be talking about the noise protocol framework. And to be exact, it's using some specific handshake pattern from the noise protocol framework, which is IPSK2. And what it does actually, its security goals is that it does provide this authenticated encryption and forward secrecy, mutual authentication, both client and server can mutually authenticate each other. It can be resilience against key compromise impersonation. That's basically, if I may elaborate further, what does it mean is that if someone steals your long-term static key, private key, for example, it tries to mitigate that kind of problem. Even if they do it, it will be very difficult for someone to impersonate one of those ends. resistance against replay attacks, session uniqueness, and identity hiding. And this identity hiding is very interesting, and I will be talking about it, how it does handle this identity hiding. And one of the nice things about WireGuard, at least if you look at the Linux kernel implementations, I mean, it's like 4,000 or 5,000 lines of code. It's very small implementation and so on. I think that's what makes it very interesting and also very efficient and so on. And also, there are also some user space implementations as well, such as Borrington. A little bit about the noise protocol framework. As you know, it was designed by the famous cryptographer Trevor Perrin. He's also well known for his work on the signal protocol together with Moxie Marlinspike. And that has been, at least has been stable too since 2015. As a side note, folks, the noise protocol framework is not a protocol. It's a framework. It's basically a framework for building these authenticated key exchange protocols. I mean, when we think about the secure communication protocols, whether it's TLS, DTLS, or well, OpenVPN or WireGuard, or in case of IPSec, we had this IKE level, etc. So there is a level that the parties need to authenticate each other, and after this authentication, they need to exchange some key materials and some cipher suites and so on. And later on, they can move forward with this protection of this data to be exchanged between parties and so on. So that framework allows you to pick one of those handshake patterns with different security properties, and you can use them basically to build your secure communication protocols or secure channel protocols. As I mentioned earlier, WireGuard is using this particular handshake pattern. I will a little bit explain to you what is happening here. And also, one of the things that I did mention that WireGuard is very efficient. I mean, one of the things what you will notice first, and I'm sure that you may have already seen that one, speed is very fast, right? Because of the fact that it uses very efficient algorithms, it's very small implementation, and so on. It runs on top of UDP and so on. That's all good. And we should also keep in mind that, I mean, WireGuard doesn't have cryptographic agility, just like other protocols. Like, you don't have choice. You don't need to decide which ciphers are, you just need to stick to those ciphers. So is it a good thing or bad thing? I mean, it very much depends, right? I mean, sometimes it can be a good thing. Some people may think that it's not a good thing. But yes, I mean, at least it gives you a kind of like, there is no room for error. At least you cannot go and start using some weaker ciphers or unsecure ciphers. At least you need to stick with them. We know that those algorithms used by WireGuard, they are known to be secure, at least as of now. So a little bit about this. So this handshake pattern, like this S letter stands for static keys. It could be like, for example, static elliptic or Diffie-Hellman keys. E stands for ephemeral, PSK stands for appreciate key, and so on. And those three dots means that both parties, they do have their prior knowledge of their static public key. So first, maybe if I may elaborate further, I mean, WireGuard, I think it's very nice protocol as far as I can see. But one of the things is that what it does not do, what many other protocols do, is that how you do establish this trust here. I think that becomes the Achilles heel when you are using this WireGuard protocol. Like, how you can exchange these static keys in advance in a secure way. How can you exchange this pre-shared key in a secure way? I think that is very important. And if that part goes wrong, I think it doesn't matter how secure the protocol is. I think this is something that probably we may see some more activities happening to make that part much easier and so on. But yes, if back to this handshake pattern, this S letter means static keys. They are known by both client and server in advance. And what happens is that client is going to initiate this will trigger this communication request by basically sending a message, which includes some timestamp and so on. But in addition to that, it does include this ephemeral elliptic or Diffie-Hellman public key. And this ES means that it is going to derive a key by using server's static public key and its own ephemeral key. It will use that key to encrypt its public static public key. That's how it is doing this identity hiding here. So anyone who is observing this communication will not be able to see the identity of that particular client, for example, because it's encrypted. And then there will be another key derivation based on static to static and so on. And then as a side note, like I did mention here, is PSK here. The PSK pre-shared key will be used, for example, for key chaining here. So eventually the keys to be derived by client and server in the end, this can also be, I mean, this PSK will be added into that key derivation by using this HKDF I did mention earlier. And the server will respond with its ephemeral public key. There will be some ephemeral to ephemeral key derivation, static to ephemeral, and then that will be done by using PSK. So as you can see, they're using this PSK quite nicely here. I mean, that's how they are actually. There are two levels of authentication here based on pre-shared static public keys, and then someone still needs to have this PSK for being able to derive this particular, for being able to break this communication. So that's basically something that to keep in mind. The setup that I do have, it's very easy to set up this WireGuard. I mean, you can either build it part of your kernel, when you go to the kernel menu, make menu config, you can build it and so on, or you can just simply go and install this WireGuard package, which will install some kernel module and so on. And in addition to that, you need to install this WireGuard tools. You need to generate those keys, you need to generate those pre-shared keys, etc. Make sure that you need to configure those client and server accordingly. And once you do that, you are good to go, basically. And that's how it is. It's very simple, and it's very fast when you. So one of the things that I will actually when it comes to summer, I will tell you more about this. But I think there are some certain areas that this WireGuard can be really useful, especially when it comes to constrained devices, for example. And IPSec. I mean, IPSec. I think we all know IPSec. It has been used for a long time, and when we think about IPSec, of course, I did mention here IKE protocol, ESP, like the Internet Key Exchange, also known IKE, also the encapsulating security payload, ESP. But of course, there are some different kind of like maybe solutions that can use, for example, host identity protocol, and then you use ESP and so on. But nevertheless, it is one of the well-known VPN protocols. It's very well standardized protocols. I mean, these are some of those RFCs. But when you look at, for example, the relevant RFCs, I think you will see dozens of them. It's very well standardized protocol. IKE v2 is covered in RFC 7296, and ESP is covered in RFC 4303. And as I mentioned, also 3GPP also do cover them as well. And one of the things that also briefly about IKE is that, I mean, those who are familiar, I'm familiar with the TLS handshake, it's pretty much achieving the same thing, okay? And there is this IKE essay, this is called security association. So typically there is a kind of user space daemon can actually do this kind of like with this handles, this key exchange. And so not only key exchange, but also exchanging those cipher suites and eventually finding out the child security associations. And that can be provided to the IPSec stack, for example, that eventually essentially that will start establishing secure communication protocol. So as of now, it's recommended to use IKE v2. IKE v1 is known to be insecure. For that reason, it should not be used. But yes, IKE v2 is the version that you can use. One thing that maybe before I go to my next slide, folks, maybe I want to tell you more about the performance aspect. Okay, I haven't done perform well. Okay, I just run them and I've been using them, and so on. I can see that some of them they are clearly faster, like WireGuard versus other protocols. One of the things I would like to mention here, because performance can depend on many other things, like what kind of ciphers you are using, for example, whether or not you are using cryptographic acceleration for those ciphers and so on. So these can actually, and also whether or not you are using UDP or TCP as well, and so on. And it's a kind of, this was just a kind of side note. So the winner, I mean, that was the, okay, that's my personal opinion, folks. I would love to see your comments in the chat. I mean, like, what do you think? You think that is the winner and so on? But to me, I mean, as long as first of all, I mean, TLS and DTLS are complete. I mean, they are in application-specific protocols, whereas VPNs can be just application. It can be transparent to applications and so on. But anyway, one of the things that I also would like to mention here is that they can be all good as long as they are used according to the best security practice. And they may have different pros and cons depending on the use case. Some certain use cases may require maybe some of those protocols may fit better to some certain use cases. Some of them they don't. But of course, I mean, one of the things I also would like to mention here is that WireGuard, for example, I mean, ever since it became part of the Linux kernel since 5.6, so I think we may expect that it will gain popularity because of these facts, not that it's part of the Linux kernel. Also, it uses some certain efficient cryptographic algorithms, it's faster, but of course, there are some certain things needs to be solved. As I mentioned earlier, how to establish this trust is very important. How to exchange those keys, whether PSK or those static elliptic curve Diffie-Hellman public keys and so on. This is very important. So now I think I can very briefly talk about the demos that I would like to show you. Folks, what I have done in my demos that I would like to show you is that at least I do have this TLS 1.3 demo and also OpenVPN demo. So with my demo with respect to TLS 1.3, so what I have done here, so I am running TLS client and server. They are using TLS 1.3. As a side note, by the way, my laptop, the one which I'm using right now, it does have a discrete TPM, actually, physical TPM. I'm using it. It's also Intel SGX capable device. So I am using both of them. So I am using Intel SGX based soft HSM, also known as Crypto API Toolkit, for protecting TLS client key. And to be exact, I'm using RSA keys here. I'm actually using those Intel SGX based soft HSM to protect my private key. And on the server side, I am using TPM 2.0. This is the discrete TPM that I mentioned. How I'm using it via PKCS 11 interface. And all those, I put the links here that they're all publicly available code that you can download and use it. And both of them, they are using PKCS 11 interface. I do have one specific slide. I'll very briefly talk about it. And on the VPN side, on OpenVPN side, I'm just protecting OpenVPN client by using a kind of like, I do have this NitroKey HSM. I'm using NitroKey HSM to protect this private key. In that case, I'm using ECDSA key pairs and so on. On the server side, where I'm running, this is something that's running on the cloud, but I'm not using any kind of, it's just basic, the keys are on the file system as is. And well, the reason actually why I wanted to show these demos to you is that, folks, this is related to one of the best security, how to protect those keys. But please keep in mind that what I'm about to show you allows you to protect those long-term keys like RSA keys or ECDSA keys at rest. And also in use, of course, they will not be leaked outside of system. But there is one important thing, if I may also repeat again, as you may remember, I did mention that static keys are good, important, but at the same time, there are other keys that are generated when those protocols are in use. And how to protect them? Obviously, there are some number of ways that you can do. For example, one of them is that, well, you can use the secure enclaves like Intel SGX secure enclaves, and it's possible to run some of this entire TLS stack within the secure enclave. There are projects, one of them is an open source project called Wolf SSL actually does support it. That's one thing. Or another thing is that you just need to make sure that someone will not have access to your process memory and so on, someone will not dump it. So how you do it, how you come up with any kind, like you may use some anti-debugging solution, you can do some hardening stuff, etc. But also important thing is that here that you also need to think about how to protect those keys, short-living keys or ephemeral keys or long-term keys in use. That's very important. Very briefly about PKCS 11, since I mentioned that I use PKCS 11 interface for being able to access to those cryptographic tokens like models. So it's one of those public key cryptography standards published by RSA in 1995, and PKCS 11 has been maintained by OSS since 2013. Right now, there is a version 3.0, but most of those things, at least the ones which I'm using, they are support 2.14 with errata 01. And it does allow us to use like PKSS 11 interfaces, allow us to do these things like slot and token management, pin management operations. You can generate keys, you can wrap, unwrap keys, you can sign, verify, you can encrypt, decrypt, etc., etc. They do provide this kind of APIs to achieve those cryptographic operations. As I also mentioned in the list, I'm using this TPM2 PKSS 11 as well as OpenSC, and I did mention them in the list. So now at least I would like to a little bit show you something about how I'm using this capability. So let me make them larger. All right, folks, on the left side, TLS server, TLS client. I will just one moment. So what I have done here, I do have this engine configuration, OpenSL engine configuration, and this is basically, I will also somehow share with you those config files, but this is what I have done here. So in this OpenSL engine config file, I did define this PKSS 11 section. So that basically tells what PKSS 11 interface to use. In this particular case, I'm going to use this TPM2 PKSS 11. In addition to that one, what I have done actually prior to my demo is that I did generate keys both in TPM and also in my SGX protected soft HSM. And you can generate, and then I did use basically OpenSSL to issue certificate sign requests, and then I issued my test certificates from my test CA. And that's basically how I am running this TLS 1.3 server here. And that's how I'm using. So one thing is that, folks, I mean, when you are using those like HSM like modules and so on, they do also record those PIN number, user PIN number. In this example, I am actually providing this PIN number from here. If I omit that one, it will prompt me to enter this PIN number. So this is like a password for being able to use this particular key that's being in that. So if I list the object, like there is one 2048-bit RSA key here. I will tell you why I could have generated, well, with TPM, as you know, TPM 2.0 does actually allow larger RSA keys, but I haven't seen any TPM implemented, like at least my discrete TPM does not allow me to generate larger keys. And also on the right side, this is the client part. This is something that I did generate in the soft HSM. Again, RSA key and RSA key. So let me just one moment. I will just start 3. Yep. And I will start the client. The client is the same one. I'm going to use this. I'm going to just start this client. That again, engine here. In this engine, I'm using PKSS 11 interface for this SGX-based soft HSM. And when I 3. Okay, that's it. Okay, I would like to a little bit show you about this protocol data messages. I want to show you what's going on here. But anyways, this is between client and server. And let me scroll back to the beginning. So what's going on here now? So they did initiate TLS 1.3. So they went through this handshake phase here. So let me open this thing and then let me show you just one moment if I can. Zoom in. So this is the part that client hello message that the client sent. By the way, folks, when you look at this client hello message version TLS 1.2, it is not like if you look at this RFC 8446 there is something else here. In addition to that one, okay, these are the ciphers that was sent by my client, and also some other information, like as you can see here, server name indicator and so on. And in addition to that one, client also sent information that here supported versions TLS 1.3. So that basically tells server that I want to do TLS 1.3 handshake. And in the last one, as you can see, it's one of those client hello messages, the key share. So this is basically like X25519. This is the public key. Okay, that's sent to the server. And then on the server side, what the server does here, as you can see here, it does actually, okay, let's use that one, AES2 fits GSM sharp 384, and then it said, okay, TLS 1.3 handshake, and then in the end here also server is sending its own public key here. It's basically X25519 base public is 32 bytes. So at this point, they did exchange some ECDH keys now. So they do derive some key now by using this key. As you can see here, there's JSON, but all the data here, you see server hello, all of them, they're encrypted here. They're all encrypted. We cannot see server certificate, for example, because it's encrypted somewhere here. Okay, that's one of the nice things about this. So, but anyways, this is one thing that I wanted to show you. This basically shows how to do this. Just one moment. So I want to at least show you something that hopefully. You see, it's now, I'm being prompted now for entering this field. So I was prompted to enter this PIN number that I said basically. When I initialize this token in this SGX-based soft HSM, I enter this particular PIN number. Now, if I don't give this PIN number in the config file, it will basically prompt me to enter that one. So here is another thing. While using those hardware-based security here, I think another thing is that how can you protect this PIN number? I mean, this is like password. Maybe you don't have direct access to those keys, but you can have actually access to the operations, for example. Like you can just give it a sign this and give me the signature, something like that. So it's just a side note, it's also important to protect that information as well. So this is about TLS. And let's also run this TLS 1.2. You will see that how big differences there is in between. So let's start. Okay. TLS 1.2. Now let's stop this and let's look at the. All right, so this is very typical TLS 1.2. So like, okay, it's TLS 1.2, and these are the ciphers and so on. As you can see here, the ciphers, they do include like TLS 1.3 ciphers, they were much smaller and so on. But here, okay, client sends all kind of information to server here. This can be sent the server response saying that hello, okay, let's use the TLS 1.2 with this particular cipher and so on. And here it's sending its certificate. It does basically send this ephemeral key. It does this, it generates this ephemeral. In this particular case, it's using this ECD ephemeral elliptic Diffie-Hellman. It will send it, and it will ask client to send certificate in return, and it's done basically. And in return, client is going to basically send its certificate as requested by the just one moment, let me show you the certificate message. And this is the certificate I issued myself for my testing purposes and so on. That's the certificate that has its private key protected by SGX-based soft HSM. And then client is going to key exchange. It will basically send its own ephemeral Diffie-Hellman key and public key, and then it will basically sign this thing. That's the place, by the way, where it does the real signing of these handshake messages. And then eventually they will say, okay, change cipher spec. That's it basically. Then at this point they switch to the cipher like AES GCM in this case for authenticated encryption. So that's basically how this TLS protocol works. And now I would like to show you how to use how to use. Just one moment. This is, by the way, folks, I want to show you at least WireGuard now very quickly. I have just a couple of minutes. But anyway, before just one moment. As a side note, like when I'm checking here, so I am running this one in my VM, okay? And but one thing that I have done here is that, folks, if you look at here, like I actually mapped this Nitro key HSM to my VM, so I can at least access to my Nitro key HSM in my VM now. So I did actually create a key inside this HSM, and then I issued my certificate, and by using this PKCS 15 tool, I put my certificate into HSM. And so that's basically something that I will be using with OpenVPN demo. But before that one, let me show you WireGuard. So WireGuard, wire. Okay. This is the server side. That's what I'm using on the server side. And okay, on the server side, and then let me is on the client side. So a little bit show you how it works. Like as you may remember, when I was talking about those, what are the things like they need to exchange their own static keys in advance. I mean, this is the public key of the server, and basically of that server, and this is the public key of the client that belongs to the client, and so on. They use the same PSK, as you can see here. That PSK is used that one. So that's basically how it works. And let's do up. That's it. And then that side. Just one moment. Okay, done. So now the server that I'm using basically is located somewhere in Ireland or somewhere. Let's see. You see, it's basically it's from Ireland. It's basically I just made a kind of like VPN connection by WireGuard to my server running in somewhere in Ireland. Let's do one thing now. Close this and shut down it. Okay, and now if I look at this, now you see now it's back to Finland again. So, but anyway, this is how it is. So one of the things what I do here is that, folks, when I establish this communication WireGuard and so on, I am basically updating the routing table here. I bring up this WireGuard interface. I basically change this routing information. I basically route all this traffic via WireGuard interface. And of course, I'm adding one information that in case if something happens, I'm basically letting it to access to the server and so on, so that it can reestablish its communication. That's how it is basically. And let me also shut down the server on the, all right, done. That's basically the WireGuard. And now this is my server configuration, OpenVPN server configuration. I did actually issue my test certificates and so on, but anyway, I did configure this, what TLS cipher to use, what kind of cipher it will use for encrypting the data channel, etc. and so on. And it can bring up some interface up and down and so on, and sudo OpenVPN server config file. So it's now up and running now. The server is up and running, and then let me come here and OpenVPN, and let's do like that. Okay, now it's not blinking on the HSM. It will. Okay, now it's. All right. Now it established the secure channel now. So what happened now is that here, okay, it prompted me to enter this PIN number because this HSM had my private key. And so let me show you what's going on here in the beginning. All right, that's the place. They actually start making some kind of establishing communication with each other. And as you can see here, I mean, they are doing some encrypting the control channel encryption by using TLS crypt v2. And but right after that one, that's the place that, as you can see here, it's basically got information about. So that's the point that I did enter my information like PIN number. It did go through this TLS 1.3 handshake here. And that was the point, basically. It was asking me to enter PIN number, and then the server got the certificate here. It validated it. It all looks good. And as you can see here, they used the TLS version 1.3 by using the cipher that I basically mentioned in the config file. And that's it, basically. And then after that, I will show you something now. Let me open another window here. Now there is a channel now right there. Just one moment. Anyways, so anyway, this is basically the end of my talk, folks. I'm a little bit 5 minutes over, but well, that's what I would like to I wanted to show you today. I hope that you found this session useful. And that concludes my talk. Thank you so much, folks.
Thank you very much, Ilhan. We have a lot of questions for you.
Oh, cool.
So let's see them out. So the first one, what's your opinion on Camellia? Camellia. Not sure how to pronounce it.
Camellia cipher, right? Camellia. I have never used it. I have no opinion about it, but I think, is it so that there are some kind of patents or all kind of things behind it? I haven't used Camellia cipher, but quite possible. Maybe there must be, probably, like I said, either there is some kind of patent things behind it, or there is some kind of like some certain terms and conditions behind it, but I have never used it.
All right. Thank you. So next question is about the TLS, and is it the standard community already considering quantum resistant algorithms?
I think that's if I may actually show something here, as I mentioned earlier, the NIST has been now doing some standardization activities. At least I put the link here. Now they are now this is the third round now. So there are some certain finalists and so on. I think it's expected to be completed by 2024 or something like that. But yes, it's where I think nothing will happen until the NIST makes some conclusion there. But of course, there are some candidates, at least Picnic and Frodo KEM is one of those alternate candidates, but there are some more to that. I put the link here. When they receive the slides, they can have a look at it. But with respect to, I mean, if they go to those links, there are some already implementations that they can also try with some of those candidates. For example, they can see in real life how to use them. But yeah, I think probably we will see something happening after the NIST concludes their standardization activities. That's how I see it.
All righty. Would you recommend developers to create their own encryption algorithms?
Of course, no. Of course, no. I mean, this is. Here is the thing. I mean, this is not a, well, obviously. The straight answer is no. I mean, obviously, no one should do that. I mean, this is because writing this kind of algorithm, like, okay, forget about this. I mean, this requires lots of when we see many of those cryptographic algorithms used by, they were designed by very amazing genius cryptographers and so on, yet they end up being broken or something like this. Okay, this requires lots of competence. I mean, someone who knows those things needs to do it. But there is one important thing here. Designing one algorithm is one thing, implementing this algorithm is another thing. And then how you do this implementation, there are lots of things can go wrong. It's not only that you can be really an expert software developer, yet you can end up writing very extremely vulnerable cryptographic implementation, because that's something else. You need to know all kind of things like how things can be leaked by means of side channel leakages, all sorts of things. And I mean, this is an art, I mean, this is writing some crypto code is an art. Not everyone can do it.
Yeah, of course. Next question about the hosts, the 34 vulnerable hosts to Heartbleed. How many of those were honeypots?
That one I don't know really. I mean, I just basically looked at this. It's quite possible that maybe nowadays we see lots of deceptive technologies emerging and so on. You may be very well right that they may be one of the deceptive like honeypots or however, like breadcrumbs or whatever you call them and so on. But I don't know. I just basically put this information from those SSL lab statistics.
All righty. So many TLS libraries have quite loose defaults for certificate-based authentication. For example, the server hostname is not checked against the certificate subject in OpenSSL or Wolf SSL. Are there any good major materials on best practices in configuring the authentication in TLS?
I think that's a great question. And that was something I was supposed to mention during my talk. It's great that now you did mention this one. When I was talking about this trusting, I mean, frankly speaking, yes, I do agree with you. Many like cryptographic implementation. Sometimes, like for example, when you use this like APIs from crypto library XYZ, typically they implement some callback functions. People do nothing in this callback function. So that means that whatever the server certificate is sent, you can just basically accept it and so on. So before maybe coming to the best security practice here, like what guidelines available and so on, maybe let me a little bit elaborate one thing that what can be done and so on in this part. So definitely anyone, for example, who is paying attention to this kind of making sure that you will not be vulnerable to many individual attacks, you need to validate those certificates really well. Client and server, so it doesn't matter. So when it comes to server certificate validation, there are some number of things that needs to be checked. Like, first of all, valid certificate is a valid certificate. It's issued by non-CA certificate authorities. And in addition, it's within the validity period. Like there's this subject name, like common name or subject alternate name or something like that. It does basically match in case of server certificate with the domain name that you are trying to make connection. I think this is very important. And you need to pay attention to those key usages, external key usages, and these sorts of things. I think well, in addition to that one, I mean, in addition to that, server also, we have seen in those slides that there are some servers, like quite significant part of them, they use OCSP stapling. So you also may need to do some revocation checks as well. So there are a number of things needs to be checked. So are there any guidelines? Well, of course, there are some kind of guidelines who are in this business, like I mean, there are things being followed, but I mean, I am not sure if there is any kind of like really well-written guidelines out there. At least if someone finds anyone, that will be great. Like, please put it to the chat window, but I haven't seen so far anything. But like I said, when it comes to validating those certificates, there are many things that needs to be checked as far as I can see.
Alrighty. I think that was all we are going to go through in the stream, but there is a few questions more for you.
Sure,
So
I
if
can
you have
answer
time
them,
to
yeah.
answer them afterwards, it would be super nice.
I will.
I want to thank you, Ilhan.
Thank you,
for
thank you,
being with us once again.
Thank
And
you.
hopefully we can see
It was
you.
a great pleasure to be with you folks again.
Yeah, it's good to have you in the community. We are going to have a few minute break, and then I will have the final words for this virtual meetup. Thank you very much once again, Ilhan.
Thank you.